And yes, we are the men standing between all of you and the lunch. And like all of you, even we are a little hungry. But I must admit, more than that, today standing here, we feel like an embedded device where we have a predefined job to do in a given environment, live by a deadline, and are open to interaction and interruptions, but we are not open to be programmed. That's what we want to believe. So, it's like that washing machine happily idling around, and somebody goes and plays the start button, and it has to work. Today, we stand like that here. And you would have seen now there are about or heard that there are more than 16 billion devices, which also means there are a growing number of software teams contributing to make it. And with embedded, it's always been about hardware and reliability, but the way things are getting connected, the way new frontiers are being opened, software acts like a true differentiator. And today, the software practices, right, which were very dominant in IT, are penetrating very well into the OT world. We are not here to challenge anything that these big companies do, right? Let me be very clear. These are companies who have been making embedded devices over decades. They have survived industrial revolutions. So this is not to say what they're doing right, what they're doing wrong. This is to just say, as your software development grows, the need to have some practices in place to manage or collaborate people and technology helps. And the IT has been doing it for long. And today we want to share out our experience that this is possible in OT and talk of some challenges. And yeah, Parth, so are we in for it?
We are in for it, certainly, Ranjan. Thank you for introducing, and thanks, Nidhi, for the glorious introduction as well. As Ranjan talked about, right, we have around 14 billion connected devices and probably billions more which are not connected. We have played a small part in making a couple of them connected, and we would like to talk about our experience. Everything that you see around you is a robot today. I mean, my lights are controlled by Wi-Fi. Your cars run on internet, or they can run internet. My fridge can be used to play Minecraft. And with the increased penetration of these robots and devices, smart devices in our worlds, what lies at the core of it? What lies at the core is a computer, and the system, the computer, and the hardware interfaces connected to these computers is what we call embedded systems. So that's what we're going to talk about, lessons learned while making embedded systems reliable. And I want to start by giving an example, which is, oh, my ticker is not working. I'm sorry, I was pressing the wrong button. I'll be the less serious one in the talk.
It's a software-driven world.
Right. So that's what happens when devices are unreliable. Let's talk of ADAS, right? I have been in Bangalore for 1 week, not from here. And I was driving around Bangalore. And what I realized in one of the cars that I was driving is the smart features in those cars, the features that assist me as a driver. What you see here is ADAS, Advanced Driver Assistance System. I'm sure you all have heard of it. ADAS is an umbrella of features, of course. So there could be features like automatic speed limitations, automatic headlights turning on, emergency braking, or staying in the speed limit, following lane markings, stuff like that. And it got me thinking, what makes this work? So let's take with one example, and that one example is automatic emergency braking. As we call it in the technological terms, adaptive cruise control. So what goes in making this possible? The first thing, you'll have a camera sensor. You need to perceive, you need to see what is in front of you. So there's a camera sensor. You see what is in front of you. What's the next step? You need to figure out what the object is. You need to figure out if it's a car, if it's a person, if it's a tree on the road. We live in India. If it's a truck. The second step, there's a radar. There's some sort of LiDAR which will work on detecting how far away the object is and if you're decelerating or accelerating towards it. And all of these sensors, there'd be GPS and other sensors. And all of this goes together in some sort of a computer. And that computer is what works on making emergency braking possible. That's how it works technologically. We understand the flow chart, right? But I would like to give the cue back to Ranjan and the clicker as well. Tell us what goes on in making a system like this.
Thank you. So how many of us have used adaptive cruise control? No one? Okay, so at least how many of us have, say, used cameras and a sonar to park the cars? So when you reverse park, your sonar gets into action. It tells you the distance of what's close by. And you have a console where so there's a camera and you're able to see an impression of that on the console, right? This is something similar, but it's a little more on the front. But the thing that you should notice here is, it's a very simple function, right? Reverse parking, a very simple function, adaptive cruise control. But just to make this happen, there are 3 systems that are coming into play. Okay,
Second time.
One is the perception, which is telling you what the object is, or helping you form an impression of the object, or build a perception. The other is sensor processing, which is, you saw what the radar did, and helping you get the distance. The third is the control system, which Parth spoke about, is responsible for the braking. So now these 3 systems come together, and this is what fulfills what the ADAS system was meant to do. So an ADAS system would work with interfaces from perception, sensor, as inputs and generate an output to control system. Now let me help build or give a perspective of how you could look at this, right? Because it's a little important given we talk of embedded. So when you look at perception, sensor, and control, this is more like systems engineering, right? These are systems, and that's how these are developed, right? The capability is how good they are. But ADAS is more of a consumer product. It's an end consumable. So the focus shifts that how useful this is, right? While this is how good, strong, how technical, excellent they are, ADAS is how useful it is. And since ADAS is consumer, it's driven in a little different way. And rightfully, perception sensor are more about capability buildings because they want to be the best systems that exist. Now, when you start or get into a project, right, and if you belong to ADAS, you would have seen that it's very difficult getting people on board. And anybody who has done, worked on any systems engineering problem or done or built software which is more about interactions, there's a decent time that you only spend in building APIs that you could ingest, right? So nothing different happens here. And let me also tell you a scenario where when you're into building a system, you also end up facing trouble and errors. But to begin with, first things, the usual is system capabilities and individual goals. That's how they start and live by. To quote an example, imagine that you have cameras and it's sending frames. The sensor processing is doing a good job of processing it, sending it to perception for sensor fusion. And at ADAS, we realize that the rate is not right. So there are frames that are missing, or the frequency is not what we wanted it to be. And if you want to correct this, right, it's a huge cycle. First of all, this ask never would get prioritized or would take its own sweet time. On top of it, look at the validation costs, because this means the sensor needs to correct the error, the perception needs to correct, and then that whole validation change comes in, and that's when the ADAS team gets it as a consumable, right? So all of us, from product standpoint of view, when we start something, we do get into this problem of having common goals and setting the right prioritization, right? And this is the elephant in the room, because as technologists, it's a little easy to navigate technology, but it's not so easy to navigate people and processes, and I believe you'll agree with me. Now, we spoke of so many inputs and outputs and software, so different versions. So different versions just to build it, but look at a car. A car has so much of software in it, and as you all know, different cars, different variants, which means you may not get cruise control, say, when you buy something worth 6 lakhs, but you may get it when you buy something worth 12 lakhs. So again, multiple versions to manage also at a deployment level. On top of it, when you ingest somebody's work or as a foundation of how you yourself build your work, there are problems that happen. And I think all of you sitting here would have a lot of experience with embedded systems. And I'm sure you would have seen processes getting killed, sensors restarting, build failures happening. I don't think anyone has been away from this world, and I think we're very happy. We just restart and we carry on. But I don't think we should look forward to such methods as we get more and more software in. And more importantly, there is also a lot that, say, the development mechanism offers, or maybe the controllers that you use, and the programming interface that it offers that helps you deal with this, right? Because some may deal memory in a more static way, and some might deal in a little more dynamic fashion, creating trouble. But in all, this is the scenario, right? I don't think so any of us has escaped this. So now, when we build something, it's about people, process, and technology and nothing else. So we just wanted to bring this view to tell you that dealing with the elephant in the room starts first with stakeholder management and methodology workflow. With management, I don't want to bring this or make this any big. And I'll tell you what I mean, right? It's really more at execution, what is it that we should do. It has helped us, and we believe it should benefit all of you too. Technology, we believe, is fairly straightforward, right? Like, when you're building something, these are the little capabilities we need. This is what we should do for app building. This is how we want to validate it. And overall, I think we are a little less focused on developer experience, which should be the crux because they are the ones who are building it. And you should give them the right tool set so that they can build and deliver it right and contribute to the reliability, which is the core of embedded systems, or if I may say, most of the manufacturing sector also. So let's try to navigate this through people and process and technology framework, if I may say, because that's what goes into making this. So imagine, instead of having these siloed approaches, right, if we had a mix of teams where people from perception, sensor, and control took direct interest in building ADAS, which means all of them as a team signed up for the common goals. And I don't mean the project managers here or the leadership here. I mean the people who are actually working. So which means you have developers or tech leads or somebody with decent authority on repos working and contributing and facilitating work so that you can easily manage dependencies. The benefit this also has is you would also see a lot of cross-pollination of good practices because what's good here gets transferred into the other system. Likewise, as I said, right, the developer experience matters. So having good methods to homogenize things and give it to the right set of people who could help build it does make a difference because there will be somebody who can cross-breed different development practices and make the best come. So it's good to have some foundations through DevOps teams and more make it like a platform offering. These are some of the templates that we used to get into or get sign-ups for common goals. We have more such and we can talk of it, but the basis or essence is that when we are all sitting together, we might have different understanding, different definitions. So as a first step, come together, do that. Make a workflow of what is it. So what is the definition? What is needed to make that happen? Then you kind of discuss, you kind of streamline, you kind of get a flow out, then you kind of prioritize it, and then you kind of build a high-level architecture, and you understand also what the components are and who are the people you could contact to. More often than this gets missing, though it's so simple and so straightforward. It is a missing piece. At least we have seen it. And it's more because of the ways of working, right? And nothing else. Along with this, you may also conclude here, right? How do you want to run your boards? How should people participate? So you set up some governance principles. You set up the methods of interactions. The good part is, right, the actors are collectively participating and bringing things together than somebody just pushing it down. So the difference is, it's very simple, but the way you do it is different, that the ones who are involved are the ones who come together and make this happen. And there are more such templates, but as a consequence, you have seen that you have a team organization in place, you have featured aligned teams. And we have seen that when you begin with, right? So you may have perception team, sensor team, or say a hill team, right? their participation may not be so much. But when you run more such murals, such meetings, and people sign up for common goals, you see as a consequence, autonomous teams starts to form. And when that forms, you would see that they would take care of their continuous learnings and growth. Instead of really having a skill set matrix and pushing that, now you're moving to a natural evolved method where people know what the goal is and what are the necessary ingredients needed to fulfill it. So a bit of gyan, right? But it's important. It's the elephant in the room. This is where most of the trouble happens, whether you like it or not, or agree or not, right? So from here, I think let's move into the technology, because a lot of this is enabled by technology. And I think Parth would take you through all of
Right.
that.
So we covered the manager's perspective, right? I want to cover the engineer's perspective. So from people collaboration, let's jump to the tech collaboration. When you're building software in distributed teams, especially teams that are distributed when it comes to embedded systems, there are different tools, methodologies, technologies that different teams use. And we needed to find a way to bring this together, to homogenize this. Because we heavily rely on C++ for building our software in particular. The build software used to rely on Bazel, on CMake, on Conan. Some of them would be shared using Docker, some of them would be shared in a repository. And the running format, right? The tools, technologies, all of it was different. What we've implemented now is Snapcraft and Docker. So these are two technologies that we want to talk about. Docker is something that everyone is familiar with. It gives you a common environment for development. So all your core sensors, all your drivers, or your core interfaces are available to all teams, and you can make sure that it's the same format. So we use Docker for intra-team communication. Now what is Snapcraft? How many of you here have heard about Snapcraft? No one? Okay, you should check out the Tech Radar published by Thoughtworks. It's the volume 34, Snapcraft is mentioned there. So Snapcraft is featured in the Tech Radar. Snapcraft is a way to package your Linux applications, and it's like you package it once and it runs on all Linux machines. So when you're running anything on Linux, the Snap daemon is already available. You don't need to install it separately, and it just works out of the box. So that's what we used for deploying our software, and not deploying to the customer, but deploying to the VNV team, which is validation and verification, or even to the customer teams for testing. We build snaps, and we publish them in an internal artifactory. And all of this is supported by enablement teams, as Ranjan talked about previously, which is there is a team that supports the Docker environments, there's a team that supports the other platform offerings such as Snap. Moving on, I said C++, and I know some of my colleagues from the earlier talk would frown at it and say that why don't you use Rust, but we can't. So one of the biggest problems of C++ is memory leaks. And there's a tool called Valgrind, which we've implemented. It's an open source tool that's available, but we've implemented that in the pipeline. I don't know why the demo is not running. That's fine. So Valgrind is a tool that checks for memory leaks. And these memory leaks that can happen, so you forget to dereference a pointer, and the memory leak happens, right? And the memory leak could be very small. So someone running your system in a cloud environment would not care about a 40 KB leak or an 80 KB leak. But for us in the embedded space, where memory and storage and network, everything is constrained, memory leaks matter a lot because they hog up your memory. And they can kill processes, which we talked about earlier. Linux has OOM killers. Have you heard of OOM killers? Linux devs? No one. OOM killers, so what happens when you overload a process with memory is that the OOM killer kicks in and it kills the process. That's what kills the process running in any Linux device. So we've implemented Valgrind to catch those in the CI pipeline. And the second demo, which we had, which I'm sure will also not run, and the clicker is also not working. Can we check this? Can you move the slides manually? Oh, we did. It's back. So the other thing that we did, and Ayushi is the name of our teammate who we asked to implement these and put in the demo. We apologize for not being able to run those. But validation pipelines. So because we consume a lot of content from different teams, as we talked about, as soon as a release is created for those teams, we would run some sanity checks, and the sanity check would let us know if the content is consumable or not. So that's another thing that we've implemented in CI. What does all of this achieve? And we've all looked at the test pyramid one time or the other. Are there any QAs in the house? No one. So this is a test pyramid. And the test pyramid is, you see, it's fat at the bottom, which means that most of your testing should happen at the unit level. And as you move up the ladder, which is at the integrated level, or the system integration, or the user acceptance level, your number of tests should keep on decreasing. What happens with embedded is, because a lot of the hardware interfaces that we need to run our software is not present, the tests that need to run at unit level are very less. And that is why the number of tests increase at the levels above, and with that, the number of defects that are caught at levels above increase. Why is this problematic, right? You'd ask, why is this problematic? We are still catching defects, right? It's problematic because the time it takes for a person, the team, to fix that error increases as soon as you go up the ladder. So if your software is in the user acceptance level, as soon as you find a defect, you have to go back all of these levels, fix it, then run it through all of these levels again. So what we tried using some of the demos that we showed or could not show, but we talked about them, and some of the other tools, for example, SonarQube, which is used to figure out code smells, gtest and gmock for testing C++, classes and modules, formatters, linters at level 1. Then there's Valgrind for memory checking, test data management tools, and DevOps tools like Azure DevOps at level 2. And similarly, for level 3, we have dummy data publishers, data analytics for scenario generation, the simulation, the software in the loop, hardware in the loop, performance measuring tools, and Snapcraft that we talked about. All of this has led us from finding 70% defects in L4 to now finding less than 20% defects in L4. And that's the benefit. And we showed this slide when we began, right? Which is, what did we act on? And Ranjan covered some of them when he talked about his perspective, his side of the story. Here are the other things that we have talked about, and these are the outcomes of that. But you'd say, what came out of it? What is the one thing that we can take away? I would like Ranjan to answer. Ranjan, what did come out of all of this?
So we ended up improving our software implementation cycle time by 50%. So how did we do this, or why did this happen? So if you look back, right, we first of all spoke about the delays that prioritization and all could cause. So having the right team helps you achieve goals in time. Certain tools like SonarQube, right, Valgrind. SonarQube would help you with linting, formatting. It would also help you implement Mishra guidelines, which is for C, C++. It'll help you say what are the reliability and maintainability issues. So all this is automated. It does save your time. In terms of test crate creation, so there are data which can be generated once and used multiple times. Then we have gtest, we have code coverage. So things like code coverage and all only helps build a little bit of a surety, right? That everything that you have written is kind of tested. So all of this, when you try to put this into practice, you are able to see that certain things move faster than before. So we really had a time where we used to take 20 days to finish a story, and now we take 10 days, 8 to 10 days to finish a story. And the point I also want to drive is you just can't keep on optimizing. So when you implement these practices, the first jump is very quick, then it gets a little lower, and you should stop. There's no point breaking your head more on this. What you could next move on to is optimizing this entire flow that you see here. And we kind of have estimated that if you, kind of spread this methods, then keeping the capacity same, because we are not here trying to say that you should have less developers or more developers. Living up with the capacity, you would see that your product can go to the market a little less sooner, right? So we have seen that the TTM can be reduced by 30%. TTM is not the goal of, if I may say, hardware software development, right? But what we want to drive home is that this is possible, right? We are not here to poke the reliability side of things. We are just trying to say that TTM is possible. We are trying to say that Docker is possible here. We are trying to say that Snap is. So containerization and making that happen both at build level and deployment level is possible. And of course, we are not talking of very small embedded systems. We are talking of fairly large, right? And maybe you could also explore other OSs like Zypher. Zypher is catching up. Zypher can be containerized too. So there is immense effort going in to promote this and have all of these things available at container level, because it is a game changer, right? So in all, there are benefits that we have realized, and since as a part of process, right, like I said, it's important how do you want to work. So Agile has many aspects. We started to move ahead with Kanban, and we started to bucket work as Scrum. So when we started to move as Kanban, cycle time was the obvious choice. So this is how you agree, you decide metrics that matter in project management, and likewise your Sonar Cube, what your threshold should be for build failures and stuff like that. So moving on.
So we've optimized SDLC, right? We've brought down the cycle time. But is that it? Or should we do something else? And that's what the next section is about, which is about observability. Ranjan, do you want to cover it?
Sure, I can. If you want me to. Like when you look at embedded device, right, it's not open at all. So how do you understand what the trouble is? So you deal with printers, right? So with printers, you could see the error codes and kind of understand what the problem is. Maybe it could be cartridge replacement and get that done. So these are about machine events and error codes, how they can help you. Traces is more about, as I said, multiple software versions. So it's good to have a trace of which version was installed in which hardware, so that when there are bugs or when there are problems, you know what the source is and you know what the mode of thing is. So our tracing here only is at Git software level to the deployment. We don't talk of anything beyond that, like what doors or other tools do. Likewise, let me give a quick example of functions and traces. So imagine your mobile, right? You end up banging it or you end up hitting it hard. There's a vibration log that's created, which might kind of create troubles for you when you go in an exchange mode. So the manufacturer has kind of accounted for that and is able to well take care of what exchange rate should be charged. At the same time, it's a good gauge to understand how much of it is a user usage problem and how much of it is a design problem. And then consequently, what can I bring back in? And performance logs, likewise, right? So while you may design and test for performance, I think usage scales it to a different level. Good to have that. The point is the embedded is restricted. Now there are technologies in place that can help you create logs and log those and actually analyze those. So this is possible regardless of how small or how big your device is. And this is very important. It helps you deal with warranty issues. So I hope I've answered you.
You have, yes, let's change places for the photographs. So we talked about all of this, right? Let's circle back, let's summarize. Let's categorize what we have talked about and quickly talk it in 1 or 2 lines, because there's a lot of stuff that we put in the presentation. First thing, the product thinking approach. What is it? Move from system capabilities and individual capabilities to product capabilities. What does it mean? It means that think about what are you building that is going to end up in the hands of the consumer, and start tracking back from there. So product capabilities over system capabilities. That's the takeaway from product thinking. Second, shift left practices, which is implement as many tools and technologies you can as early as you can in your software development lifecycle. What this will help you do is find errors quickly and fix those errors quickly. The feedback loop of fixing an error will be small. You'll save cost for the client, for yourself, and the team from a lot of stress. And the third thing, observability, which Bharani also talked about in his keynote, traces, logs, and metrics, right? You have traces, you have logs, you have metrics that your application generates. It is there for the consumer, so once your product is out in front of the consumer, there is observability for sure. But once you develop that framework, it also comes back and helps you in your SDLC, in your software development lifecycle. So it's still a lot of categories, right? Let's categorize this into one. What are we talking about? We are talking about engineering effectiveness in embedded systems. And engineering effectiveness has been talked about a billion times in the IT world. We want to bring it to the operational technology world, and we don't only want to bring it, we have some experience in doing that. And that's what we wanted to, if you can have one takeaway from the talk, right, it should be how you can implement engineering effectiveness practices. And I would like to circle back to Ranjan to talk about how do teams evolve in their engineering effectiveness measure, and how does the team measure where they stand?
Okay, so I think very text heavy, so you can have a look at it for a few seconds, and I'll be quick because we are running short of time. But the essence is right. Engineering effectiveness is a journey, and you should see how you can make it at the center. And rather than learning from mistakes and each time making that up as a process, it's better to start with what the needs are and what the required tools are. So what is it that you want to change, and what are the tools, techniques that you could do? So we wanted to kind of move from a supporting role where it was completely detached to do things to center it, right? And these are little things that we did, and we could kind of declare that, look, we are at collaborative level, we are evolving now. But you may have your own journey. So the takeaway here is we have some assessment templates that can help you assess the maturity of your engineering effectiveness. At the same time, we also have some assessment sheets to let you understand the digital maturity of your manufacturing unit or manufacturing stuff. So take benefit of those assessments and build a gauge of where you stand and where is it that you want to go.
Thank you so much. So the conclusion is, how did we evolve engineering effectiveness, and how can you do it as well? Strive to progress towards focusing on the means and not just the ends. Focus on what the client needs and what the user needs. Keeping the development team close to the client to make the feedback loop smaller, as we talked about. Maintaining design principles, maintaining and propagating design principles. Cross-pollination of best practices, sensible defaults that you have developed, bring them to other teams. And assessing the value statement as often as you can, because goalposts change very quickly when you're working with softwares. And that was our talk. I'm Parth Purvesh.
And I'm Ranjan Sharma.
And we'll open the floor for questions.